Assalamu alaikum. Please settle down quickly. So what does the Compton effect tell us? What's the message, the moral of the Compton effect? थोड़ी सी आहिस्ता बात, बिल्कुल थोड़ी सी आहिस्ता करें, ठीक है, इधर ही रहना. हाँ जी. What's the moral of the story? What does Compton effect tell us? आपने अभी पेन फेंका, आप बताएं कि what Compton effect से हमें क्या सबक मिलता है? Why are we learning the Compton effect? Where does it fit into the overall picture of modern physics? आप बताएं लास्ट रो में. जी बताएं जी. The material properties of X-rays. So what are those material properties? Right. So there is a transfer of momentum from the photon to the electron. So the photon is acting like a particle. So even though light, we've seen experiments and demonstrations in which light could be interfered, and that could only be explained with the help of the wave theory of light. But here we observe that in the Compton effect, a photon is carrying momentum, it's striking an electron, it's transferring some of its momentum and energy to the electron. So the Compton effect really tells us that the photon does indeed carry momentum even though its rest mass is zero. So if we look at the Compton effect again, we have an electron at rest, and we are drawing this electron as a sphere, as a ball, a spherical shape. So this is our intuition of what we think a particle should look like. So in our 12 years of education, we have been visualizing the electron as a sphere, and whenever someone asks you to draw an electron, this is what you would draw. So it's a particle, and a photon, an X-ray photon, is also a particle, and it is carrying a momentum h over lambda dash. Its energy is hc over lambda. Its energy is hc. It strikes the electron. This electron is scattered. This is the initial direction of the incident photon. So this electron is scattered through an angle phi, and it carries away some energy. Initially its energy was just m naught c squared, and after the scattering event its new energy is m naught c squared plus some kinetic energy. Okay, m naught c squared is intertwined with the existence of the electron. Whenever the electron exists, it will have this energy of being, and this energy is also equal to m naught c squared plus pc squared, where pe is now the momentum of the electron. Both of these are equivalent expressions. But the photon is also scattered. So after the scattering process, the photon moves away and it makes an angle theta, and it carries away some momentum. Its wavelength changes, and the new energy turns out to be hc over lambda dash, and the new momentum is h over lambda dash. So this is the schematic illustration of the Compton effect. Alright? So this is just a recap of what we saw before the midterms. Any questions about this? It shows that this photon is carrying momentum, and the collision can be envisaged as a particle-particle collision. One body colliding with another body, sharing its energy, sharing the momentum. The total energy has to be conserved, and the total linear momentum has to be conserved. And we also derived another formula. This lambda dash. Can you tell me what's the relative magnitude of lambda dash and lambda? Which one of these will be greater? Which energy has to be smaller? This energy has to be smaller. Otherwise conservation of energy will not take place. Which means this lambda dash has to be greater. So there is an increase in the wavelength of the photon. So this increase in wavelength, lambda dash minus lambda, is also, let's call it delta lambda. How much does the wavelength increase? And we derived an expression the other day. It's given by h over m naught c 1 minus cosine theta. So it does not depend upon the initial energy. The change in wavelength does not depend upon the initial energy. It only depends upon the scattering angle. Now what I would like you to do is, I would like you to plot on this axis I have theta, and on this axis I have delta lambda over h divided by m naught c. So I'm just taking this factor to the other side. I would like to, in other words, I would like to plot 1 minus cosine theta with respect to theta. So I'm just doing a normalization. This constant, this is a constant, h is a constant, m naught is a constant, c is a constant. So this is just a constant. And what are the dimensions of this constant? क्या dimensions होंगी इस constant की? 1 over length. The dimensions are per length. So the units are 1 over meter. So this is a very small quantity. It's called the Compton wavelength. It's 2 into 10 to the power minus 12 meters, 0.02 angstroms. It's a very small number. So the shift in wavelength is very small. Now I would like you to plot this term versus theta. And theta varies from, I would like you to draw the plot from 0 to pi. वो लिखा हुआ है डेल्टा लैम्डा ओवर एच ओवर एम नॉट सी. And also identify the critical points on the graph. Identify some fiducial points on the graph. कि कोई पॉइंट्स दिखाना मुझे ग्राफ के ऊपर, क्या वैल्यू है वाई एक्सिस पर या एक्स एक्सिस पर. ये नहीं ठीक, ये भी ठीक नहीं है, गलत, सही नहीं है ये तो आपने नहीं ठीक. नहीं, आप लोग कोशिश करते हो एक पॉइंट टेबल बनाते हो, थीटा लेते हो और फिर वो लिखते हो, इस तरह जरा मुश्किल हो जाता है. कोसाइन कैसे तो नहीं होता है. देखो ये मैनिपुलेशन आपकी घुट्टी में पड़ा होना चाहिए, इतना आसान होना चाहिए ये. हाँ, ये नहीं, इसमें कुछ सोचने की जरूरत नहीं आपको पढ़नी चाहिए. ठीक है, नहीं ये ठीक नहीं है. All right, good. This is fine. So what I would do, I have theta here. First I will plot cosine theta. Cosine theta is like this, from 0 to pi. This is pi by 2. This is pi. This is cosine theta. Now I plot minus cosine theta. I just take the inverse of this. This is minus cosine theta. I don't have to draw a table what's the value of cosine at, well, it will give you the correct result, but you will have to draw a large number of points. Now I would like to add 1 to this. So the entire curve shifts up by 1. This is minus 1, this is 0, this is plus 1. So the entire curve, this yellow curve, is going to shift up by 1 unit. So this is my curve for 1 minus cosine theta. So I can plot and what's the value here at the maximum? It's 2. At pi by 2 it's 1. At pi by 4 it's going to be about 0.3 and so on. So this is the expected change in wavelength with respect to theta. Now how does this translate into the experiment? How did Compton perform the experiment? Right? So this is a question. We really have to see the genius of the experimenters, because physics did not drop out of heavens and fell into our plate. It's not like that. There is a long list of experimenters who actually tried to verify these results. So this experiment basically works like this. First of all, one has to produce X-rays. Okay? So how do you produce X-rays? By accelerating electrons in a cathode ray tube. So you have an evacuated glass tube, you have a filament inside the tube, a current flows through the filament, and then there are electrodes, there is an anode, and you apply a high voltage, a variable high voltage to these electrodes. This is the anode. Electrons that are emitted from the cathode ray tube, they are accelerated towards the anode, they are suddenly stopped, and X-rays are produced. So what kind of X-rays will be produced? Will they be characteristic X-rays or Bremsstrahlung X-rays? They will be both. They will be Bremsstrahlung X-rays because of the sudden halting or the slow deceleration of the electrons, as well as X-rays that are characteristic of the element inside this tube, inside this electrode. Now what we would like to do, we would like to select one wavelength, because the initial wavelength has to be fixed. So we would like to select a monochromatic beam of photons from these X-rays. So Compton in 1923 placed a filter. You've already seen how a filter works. A filter selects photons in a certain wavelength regime. So it produces a monochromatic, here we have a monochromatic beam of photons, of X-ray photons. Then Compton inserted a large number of slits. These are slits. This pink object is a filter. Now the slits were introduced because Compton wanted these X-rays to pass in a straight line. in order to prevent the divergence. And then he placed an object. What he placed was graphite. Graphite is just carbon. Lead pencils have graphite. ठीक है, lead pencils के अंदर graphite होता है, उनके अंदर lead नहीं होती. So he placed a graphite sample. Now this graphite has bound electrons, it has free electrons. So this graphite provides these electrons. The X-ray tube is providing these photons. Alright. And then you place all of this in an evacuated tube. This is an evacuated flask in which air has been pulled out. Remember that most of experimental physics has flowered, has blossomed because of the invention of vacuum in 1860s by Otto van Guericke. So it is vacuum, which is the nothingness, which is the absence of air, which has led to all of these experiments. This is something very strange. You pull out air, you are able to do the experiment. So nothingness is very important in physics. Vacuum is very important. G.
What was the purpose of the graphite?
The graphite, you need to have a source of electrons. Graphite, in graphite, each carbon atom is bound to 3 neighboring atoms. But there are 4 electrons in the valence shell. So a 4th electron is free. So photons have to collide with some electrons. So this is a source of electrons. Now you need to have a detector. And what is the detector going to measure in the Compton effect? How can we get this graph? By measuring the angle. So you vary the angle, but what do you measure? The intensity of the photon. But you need to measure the wavelength of the photon as well, because you need to measure what delta lambda is. What's the change in the wavelength? So you need to know what the initial wavelength is, what this wavelength is, and you need to know what the scattered wavelength is. So you need to have some kind of detection mechanism that measures the wavelength of the photon. Okay? So what you really need is, this is the line of incidence. You need to have a detector maybe outside this tube. Again you have slits. So photons, they are scattered and they pass through this slit, and these slits can vary their position because you want to vary the angle. So these slits can be here. When these slits are here, the angle is theta, and then you increase theta. So you can vary the position of the slits along an arc. Here the angle is 90 degrees, and here the angle is 135 degrees. Eventually here you get 180 degrees. So you can vary the position of these slits to select X-ray photons that are scattered off at an angle theta. Agreed? Because you would like to plot this graph, you would like to vary the angle theta, but now you would also like to measure the wavelength of the X-ray photons. Alright? So how does one measure the wavelength of X-rays? Please think about it. I've already hinted at this point before the midterm. We need to measure the wavelength. Energy nahi.
We can measure frequency.
How do we measure the frequency?
Use different metals and try to see which metal experiences photoelectric effect.
It's very difficult to do, because these energies are kilo electron volts, and the work function is electron volts.
We use a filter, a different filter for different frequencies. So the one which blocks all the...
But it's very hard to have filters. You see, these X-rays have wavelengths of the order of picometers. Picometers, 10 is to minus 12 meters. So you need filters that can select between 1 picometer and 2 picometers. These are impossible to make. Diffract कर सकते हैं, शाबाश. We can diffract these X-rays. I've already shown before the midterm that if you have some crystal in which there are planes and there are atoms lying on these planes, and if the planar spacing is d, X-rays shine on these planes, they are reflected or scattered, then constructive interference takes place only when this condition is satisfied. 2D sine of, I call alpha, where alpha is this angle. I don't want to call it theta now because I've used theta for something else. This equals lambda. So if D is known, and if I plot alpha here and I plot the intensity here, I get peaks. So by measuring the alpha at which constructive interference takes place, and by knowing the D of the crystal, the interplanar spacing, I can measure the wavelength. This is called X-ray diffraction. And this is how the crystal structure of DNA was discovered in the 1940s by Watson and Crick. So X-ray diffraction is a tool. If you know the wavelength, you can find what the material is, because you can tell what the value of D is if you get this diffraction pattern. If you know what the value of D is, you can find out what the wavelength of the X-rays are. So now in this case, one has to measure the wavelength of these X-rays. So one places a crystal जरा ऑन कर देंगे, ठीक है. ये क्रिस्टल है ऑफ अ नोन डी. सो दिस इज अ क्रिस्टल ऑफ अ नोन डी, and these X-rays are scattered. This is the angle alpha, the same alpha that I've drawn there, and these X-rays are scattered from the crystal in an X-ray diffraction kind of experiment, and then the intensity of these X-rays is measured, because you would like to get a diffractogram, an X-ray diffraction pattern. And how do you measure the intensities? You let these X-rays fall onto what is called an ionization chamber. It's an evacuated glass bulb, once again vacuum, in which there is a small pressure of a certain gas. So when the X-ray photons comes in, it produces a plasma. It produces electrons and ions, and those electrons and ions form a current, which is measured with a galvanometer. So you can measure the intensity of these X-rays, and by the diffractogram, by this kind of pattern that you obtain here, you can measure what the wavelength lambda dash is. So this was Compton's experiment in 1923. कोई सवाल जी? एमिट ना हो, ग्रेफाइट से इलेक्ट्रॉन्स भी स्कैटर हो रहे हैं और फोटॉन्स भी स्कैटर हो रहे हैं. The scattered electrons remain inside the graphite because there is no place for the electrons to go. If the photoelectric effect takes place, then these electrons can go out of the graphite, but then there is no potential anywhere for the electrons to be attracted. Remember, the Compton effect and the photoelectric effect take place side by side. There are finite probabilities for both events. So this is the genius of Compton, 1923, and this showed without doubt that these photons carry momentum. आइंस्टाइन का फोटोइलेक्ट्रिक इफेक्ट की एक्सप्लेनेशन मोमेंटम का कोई तस्करा नहीं करता. It does not deal with the momentum, it only deals with the energy of a photon. A packet of energy comes in, it has a finite amount of energy. It transfers its energy to an electron. Many electrons do not have their energies adding up. ठीक है, फोटोइलेक्ट्रिक इफेक्ट याद है ना, वो मोमेंटम का कोई तस्करा नहीं करता. It was in 1923 that Compton, an American physicist, performed this experiment. And what I would like to show you are the original papers of Compton. A screenshot from the original papers. देखो, मैंने आपसे वादा किया था कि this course is going to be plunged in a little bit of history as well. So ये वाला कॉम्पटन ने आर्टिकल्स लिखे थे 1923 में, और ये उस वक्त सबसे मशहूर, आज कल भी सबसे मशहूर ये जर्नल है, फिजिकल रिव्यू. पहला उसका आर्टिकल था अ क्वांटम थ्योरी ऑफ द स्कैटरिंग ऑफ एक्स रेज बाय लाइट एलिमेंट्स. कार्बन इज अ लाइट एलिमेंट, एटॉमिक नंबर 12. ठीक है, ये उसका एक मास्ट हेड है उस आर्टिकल का, खामोशी से सुने. और ये उसके पास उसने he took 4 values of theta. So here you have the angle of scattering. This is the predicted curve which you've drawn. This curve, it does not start off at 0 here because there is some background radiation, but we can ignore that for the time being. And the scattering angle goes from 0 to 180 degrees. This is a plot of roughly 1 minus cosine theta. और ये जो black points हैं, ये उसके experimental data points हैं. And these experimental data points match the theoretical prediction. So these are his original experimental results that showed for the first time experimentally that photons indeed carry momentum, and they can participate in particle-like collisions, like 2 cricket balls colliding with one another. So this is the second article that he wrote, and it's titled The Spectrum of Scattered X-rays, again in 1923. And Compton, notice he's working alone, without any student. इस तरह होते हैं प्रोफेसर. और ये उसके पास एक्सपेरिमेंटल रिजल्ट्स थे. Now this is what he sees on the ionization chamber. When the scattering angle is 0 degrees, there is only one peak. There is no change in the wavelength. When the scattering angle is 45 degrees, this is 45 degrees, there is one major peak and a slight bulge that is seen. So 2 wavelengths are seen. One is the original wavelength, which is this one, lambda, and the other is lambda dash. The question you may ask, why is Compton seeing lambda? Why is he seeing the original wavelength as well? The third graph is drawn at 90 degrees. So he sees the original wavelength, this axis is the wavelength, he sees a high intensity at the original wavelength and another peak at a shifted wavelength. 2 humps नजर आ रहे हैं इसके अंदर आपको, एक ये ओरिजिनल है wavelength, ये this is lambda dash, the new wavelength or the wavelength of the scattered photon. And this is at an angle of 135 degrees. Compton could not measure up to 180 degrees because, as you can, there are experimental limitations to moving this detector all the way around, because this is blocking space. So he measured up to 135 degrees and he observed that the shift increases. So this rightmost peak is moving to the right, which means that the wavelength is constantly increasing in accordance with the theoretical results. So these are Compton's. This is with one kind of target. This is K alpha line, molybdenum, K alpha line primary, scattered by graphite, scattered at 90. So these are two sets of experiments. Alright, so these are Compton's original results. Alright, so I move on, and I would now like to explain why did Compton observe these two peaks. Why is he observing at the ionization chamber not only lambda dash but also the original wavelength? ठीक है, ये सवाल आपके ज़हन में भी आया? नहीं? बिल्कुल नहीं. अब आया मेरे कहने पर. Are you surprised a little bit why the original wavelength is also seen? Detected at the ionization chamber. Alright, so at theta equals 0, what is the shift in wavelength? It's 0. Right? So at theta equals 0, one should only see the original wavelength lambda. This is at theta equals 0. At theta equals, say, 90 degrees, one should see a shift in wavelength equal to h over m naught c, because this cosine theta is 0, the shift in wavelength is h over m naught c. So one should see a peak ideally here, where this separation is h over m naught c. So this curve is taken at 90 degrees. At theta equals 180 degrees, the shift should be maximum, and that has to be equal to two times h over m naught c, 2 times the Compton wavelength. So one should see a peak here, where this separation is now 2 times h over m naught c, and this curve is taken at a scattering angle of 180 degrees. But what Compton observes is that even at 90 degrees you see the original wavelength. You see the new wavelength as well as the original wavelength of the unscattered photon. And even here one would observe the original wavelength. So why is some of the original wavelength leaking into the ionization chamber? Why is it reaching the ionization chamber? Now in order to answer this question, let's have a look at this formula. The change in wavelength is given by h over m naught c 1 minus cosine theta. Now what is m naught? It's the mass of an electron, and this electron is free. It's not a part of the atom. So the electron is scattered on its own. The atom does not participate in the scattering process. बातें ना करो please. ये जो electron है ये free है. It's not a part of an atom. So the photon comes and strikes the electron is scattered away. But it's not a part of an atom. But what about electrons that are bound to the nucleus? Graphite has a lot of electrons that are still bound to the nucleus. It has 3 electrons in its valence shell that are still a part of the ionic core. It has inner shell electrons that are still a part of the ionic core. So there are bound electrons as well. So this is the mass of a free electron. But if a scattering event takes place with the atom as a whole, so if this were not an electron, but a huge atom which has a very large mass as compared to the mass of an electron, the photon will be scattered by colliding with this huge atom as well, or by colliding with electrons that are part of the atom. Fine? So there will be a shift in wavelength corresponding to the total mass of the atom as well. So there will be a delta lambda equals h over capital MC 1 minus cosine theta, where m is now the mass of the atom as a whole. Now how do you compare the mass of an atom with the mass of an electron? This is much massive, which means what's going to happen to the shift in wavelength? It's going to be extremely tiny. It's going to be minuscule, very small, imperceptibly small. इतनी छोटी change आएगी wavelength में कि कोई भी apparatus उसको देख नहीं पाएगा, because no apparatus has infinite resolution. So this wavelength, this yellow peak, corresponds to scattering from atoms as a whole or from bound electrons. This blue peak is from the scattering from electrons that are a part of the atom or the atom as a whole. Whereas these peaks, this yellow peak and this blue peak, is due to scattering from electrons that are free. They are present inside the metal, but they are not part of an atom. Okay? So this closes our discussion of the Compton effect. But something very interesting. A photon. Let's look at a very important consequence of the momentum of a photon. A very important consequence. Is a photon affected by gravity? Yes, it is. We've already seen that in the midterm. So there is a star and there is a stream of photons, which is light, passing in the vicinity of the star. This stream of photons changes its trajectory because the photons have momentum, and since they have momentum, they have an effective mass. Khamoshi se yaar. They have an effective mass. It's not the inertial mass. It's some kind of effective relativistic mass. And since these are massive particles, this is a massive object, there is gravitational attraction. So this process is called gravitational lensing. Gravitational lensing. Which means that if this is the Earth and you're looking at a star, the real position of the star is here. But what you observe, what you perceive is that the star exists somewhere here. So, computer science में आमतौर पे term use होती है WYSIWYG. What you see is what you get. So, what you see is what you get here. This is the apparent position of the star. But this is a deceit. ये आंखों का धोखा है. The real position of the star is here. Gravitational lensing has changed the apparent position of the star. This giant star is acting like a lens. A lens bends light. So this process is called gravitational lensing. Now another manifestation of the momentum of photons, a very interesting manifestation. Suppose this is the earth, this is the surface of the earth. ये बंद कर दे बेशक. And you are at a height above the earth. This height, suppose it's capital H. And then you have a laser here. Now suppose this laser is producing a monochromatic beam of photons of frequency f. So these laser is shining onto the surface of the earth. These photons are coming down, right? The beam is coming down. What happens is that as this light reaches the earth, its frequency is going to change. Its frequency is going to increase just because of gravity. Now how is that possible? You see, you emit light, say this is blue light, and the gravitational pull, if it's so strong, it can convert this red light into blue light. This is what this effect is telling us. Let's see how this is making sense, and if this makes sense at all. Now suppose you treat these electrons as particles called this light as comprising of particles that we know that are called photons. Now this is a photon here, and there's a photon that comes down. There's a photon here. Now this photon has an energy which is given by HF. Agreed? So at this position, the photon has energy HF. But since it's elevated from the earth and there is a gravitational pull of the earth, it will also have some potential energy. Suppose that potential energy is mgh, where this m is the effective mass of the photon. It's not zero because there has to be some effective mass. Alright? And what's the energy here of the same photon?
HF dash.
It's HF dash. Is there going to be any potential energy term? No. So this energy has to be equal to this energy because the energy of the photon has to be conserved. So as the photon moves from a height h down to earth, so there are photons coming from that glass bulb and they're hitting the earth, the potential energy is decreasing. Because if the photon has to have momentum, it must have some potential energy as well in a gravitational field. Okay, so this energy has to be conserved. So let's write a conservation equation. HF plus mgh is HF dash. Now I take h to the other side, I get f dash minus f equals mgh over small h, where h is the Planck's constant. G.
So wouldn't there be any kinetic energy associated at
All of the kinetic energy is HF. HF is the kinetic energy. मुझे खत्म कर लेना तो फिर सवाल के जवाब देता हूँ, ठीक है? इस कैलकुलेशन में कोई खराबी? The energy of a photon, we've already seen, is HF, right? And all of this energy is kinetic. ठीक है? Plus, now this is the energy of the photon. This has to be equal to P times C, the momentum times C, because the energy is also equal to mc squared. The energy of a photon has to be equal to mc squared. Note, this is not m naught, this is not the rest mass, this is the effective mass of the photon. So the energy of a photon is mc squared, right? It travels with the speed of light, c. But this thing, mc squared, can be written as mc times c. Now what is c? C is the velocity. What is mc? This is the momentum. So the momentum of the photon is mc. Okay, and now if we equate this equation with this equation, hf equals pc. Okay, so, or hf equals mc squared. So what is the effective mass of the photon? It's m is hf over c squared. So a photon behaves as a particle which has this much mass. It depends upon the frequency of the photon. Higher the frequency, higher will be its effective mass. But this is a relativistic mass. Don't confuse this with inertial mass. The inertial mass or the rest mass of a photon is 0. Since the photon is moving, it has some momentum. Since it has momentum, it must have an effective mass, and that effective mass is given by this expression. This relationship comes from Einstein and Planck. This relationship comes from Einstein. This comes from our general common sense. mc squared is mc times c. So this is a momentum. It's mass times c. It has dimensions of momentum. So this is the effective mass of a photon. Now if I put this effective mass of a photon into this equation, I would get f g h over c squared. First question, is f dash larger or f? F. So this comes out of the conservation principle. Here you have kinetic energy. All the energy of the photon, if you ignore this part, is kinetic. This is the potential energy of the photon because it's in a gravitational field. Now this potential energy is decreasing. So this energy has to go up. Which means excuse me, the frequency has to go up. So f dash has to be larger than f. Okay? So if I take this f to the other side, I get this expression, gh over c squared. Now what is this? This is the percentage change in frequency. Right? This is a percentage change in frequency. Now how much does the frequency change? Suppose h is 1 kilometers. I have a laser that is placed 1 kilometers above the earth. This is the acceleration due to gravity, 10 meters per second square on earth. This is the speed of light. It's 3 into 10 raised to power 8 meters per second. Can you please calculate what the relative change in the frequency should be? Very small, but how much? I would need a value. क्या आएगा? 10 raised to power of the order of 10 raised to power minus 13. Alright, it's a very small amount. It's 10 raised to power minus 11%. Is this really physically meaningful? Is this significant? Can you tell me if it's significant? क्या ये significant है? इससे हमारी आम जिंदगियों पे कोई असर पड़ेगा? नहीं पड़ेगा. अब आप फर्ज करें एक सैटेलाइट है, ठीक है, इंटरनेट का पूरा नेटवर्क है, अब वो सैटेलाइट्स के जरिए दुनिया में फैला हुआ है. अब देयर इज एन इलेक्ट्रोमैग्नेटिक रेडिएशन दैट गोज अप टू द सैटेलाइट और माइक्रोवेव रेडिएशन दैट गोज अप टू द सैटेलाइट. Now the microwave radiation has a frequency of, say, 10 raised to power 10 hertz. So if that microwave radiation, this is the earth, and here is the satellite, an artificial satellite. This distance, suppose, is 2 kilometers, and there is a beam of photons, microwave photons, that goes all the way up to the satellite. The satellite does some processing and sends back a beam of photons to another location on the earth, to the internet server. This is the client, this is the internet server. The frequency of these beams is roughly 1 or 10 gigahertz. It's in the microwave regime. If you look at the change in frequency, it's going to be of the order of 1 millihertz. It's 10 to the minus 13 times this. So there is a shift in frequency of 1 millihertz. Okay? Is that significant? Yes, it is significant. If it is really significant, if you have precise, now if you have multiple scans of this beam, say you scan 1,000 times, then that difference is going to be 1 millisecond times 1,000, 1 second. This is really significant. If you would like to measure time, there is a GPS timing system which computes the inverse of this frequency, which is going to be a time period. That those clocks are all going to turn wayward. So this indeed has an extremely significant effect on our lives, on our daily lives. Imagine the air control system, the air trafficking system. If all of these times went off by a second, and there are, say, 100,000 flights every day from from Dubai International Airport, there are 1,000 flights every day, and there is a 1 second lag in each time communication. Remember, just imagine, it can cause havoc. So this looks like an imperceptibly small shift in frequency, but it has major consequences. And all of the satellites, all of the communication mechanisms have this concept of relativity built into their design, built into their algorithms. So no communication, no electrical engineering, if you really want to do communication, is complete without a good knowledge of relativity. So it's all have to do with the momentum of the photons. Another example. This effect that I've shown here is called gravitational redshift. Redshift because red is generally considered to be a smaller frequency than ultraviolet, so redshift means that light is moving towards smaller frequencies as it is moving away from stars. Let me give you another very interesting consequence. For this, I would like to use a new blackboard. Suppose this is a giant star, a very large star of radius Rs and of mass Ms. Okay? The beauty about physics, what I like about physics, is that it's the same physics that is describing the subatomic world and these massive objects. It's the same physics that is describing the microcosm and the macrocosm. It's the same physics. This is the beauty of it. No other discipline, no other science matches the universality of physics. You see, if this is a star, this star is emitting, star is a star because it emits light. It's luminous. Photons emit हो रहे हैं. ठीक है, फेंक रहा है photons universe के अंदर. Now you are at a very large distance. And the photons are being emitted. What's going to happen to their frequency as they move away from the star? The frequency is going to decrease. right? Don't take this change in this could be assumed to be the waves, and don't take this to be literal. There's a change in frequency. Here the frequency is f, here the frequency is f dash, and this f dash is smaller than f. वो inverse case था, वो अर्थ की तरफ आ रही थी चीज, एक मैसिव ऑब्जेक्ट की तरफ फोटॉन्स आ रहे थे, यहाँ मैसिव ऑब्जेक्ट से फोटॉन्स बाहर जा रहे हैं. अब देखो, we would like to apply the principle of conservation of energy. The potential energy here is, can you tell me what the potential energy is going to be? The mass of the photon is small m. यहाँ पे potential energy क्या है इस फोटोन की? मैकेनिक्स याद है? बताओ. माइनस कैपिटल जी ms m over rs, ठीक है, प्लस the kinetic energy of these photons, which is hf. This has, now suppose this distance is r, right? You're far away from the star, very far away from the star, which means r is much larger than rs. You can't be very close to the star because you'll die. So you are far away from the star. So what's the total energy of the photon? It's going to be minus g, बताओ, ms m over r plus h f dash. All right, I'll just do that in a minute. Now f is larger, so I just take this to the other side. I write hf minus f dash equals g ms m 1 over rs minus 1 over r. Now r is much larger than rs, which means this is much smaller. I can ignore this term. ठीक है? So which means f minus f dash equals g ms. What's the effective mass of the photon? It's hf over c squared. H cancels out, I have f over c squared into rs. Now I take this f to the other side. This is just a relative change in frequency. Alright, if I don't want to take it to the other side, what I would like to write is, I would like to shift this a little bit. I write f minus f dash equals g ms f over c squared rs. I go to the other blackboard. I write this as f dash equals f1 minus g ms rs c squared. Are you with me on this expression? ठीक है? अब आप ये देखें, if this thing is smaller than 1, if this object is smaller than 1, f dash is going to be smaller than f. But what if this object is larger than 1? What's this frequency going to be? It's going to be negative. So does that make sense? देखो पहले बताओ इस एक्सप्रेशन की समझ आ गई, इसकी डेरिवेशन की? आप पीछे जो बैठे हुए हैं बताएं, समझ आ गई? नहीं? कहां से कौन सा? ये वाला एज? ये नहीं पता चला कहां गया? ये वाला एज है, hf minus hf dash. इक्वल्स, इसको मैं उधर ले गया, ठीक है। अच्छा, फिर मैंने क्या किया, f माइनस एफ, इस एज को मैं नीचे ले गया, वो कट गया इस m से, m के अंदर भी एज, ठीक है जी। They are the same.
What they change because it depends on frequency HF over c square at a distance of r, the effective mass of.
So what I have to take, I have to take the mass of the photon which is emitted. This is the mass of the emitted photon
Even at the distance.
at the distance. Yeah, it's the same mass that is applicable there. I've taken the mass of the emitted photon. ठीक है, that is A. इसीलिए मैंने ये जो मास है इसमें F है, F डैश नहीं है, ठीक है। जब भी F होगा उसके साथ मास M है। अगर यहाँ F डैश होता यहाँ और मास हो जाता। देखो तवज्जो से सुनो, जब आप मंजिल के करीब पहुंचते हैं तो ज्यादा बेताबी से मंजिल का इंतजार करते हैं। ये इनका सवाल था कि now the frequency is changing, isn't the mass changing? Yes, the mass is changing, but whenever I have F, I have M. If I have F dash, I will have M dash. Okay, but I'm using F. I'm substituting the value of M given the frequency is F. ठीक है, ये वाली एक्सप्रेशन मैं सब्स्टिट्यूट कर रहा हूं। So now this is the final expression that I get. Now if this term is, if it is greater than 1, then this term becomes negative. And what's the meaning of a negative frequency? Light does not reach at that point. Very good. Now let's look at this a little bit more. What this means is that if G over C squared into MS over RS is greater than 1. In other words, or MS over RS is greater than C squared over G, F will be negative. Now this means that if this object is larger than this object, now let's look at the size of this object. This is C squared, this is of the order of 10 raised to the power 15, 9 into 10 to the power 16, or it's 9 into 10 to the power 17, right? The numerator. This is 6 into 10 to the power minus 11. So this becomes almost 10 raised to the power 28. This term. And what are the units? What are the units of this term? हाँ, किलोग्राम पर मीटर्स। जो इसके यूनिट्स होंगे, जो इसकी डायमेंशन है, वही इसकी होंगी। So this is kilograms per meter. Now this is a kind of density. It's not kilograms per meters cube. It's kilograms per meter, but it's a kind of linear density. It's not a volume density. It's a linear density. How much does 1 kilometers of length of the star, how much mass does it contain? It's a kind of linear density. So if this object, the mass over the radius, which is the linear density, is larger than this value, F dash will be negative. And this means that light will not escape from this star. If this object has a very large value of ms over rs, which is greater than 10 raised to the power 28 kilograms per meter, then light cannot escape from this object. So this object, star or some kind of heavenly object, will not, even though it's luminous, it is not giving out photons. Such an object is called a black hole. And the black hole must have densities, linear densities greater than 10 raised by 28 kilograms per meter. In fact, a similar calculation was done by Subramanian Chandrasekhar when he was only 17 years old. And he was going on a ship. He had nothing else to do. He was traveling from India to England for his PhD studies, and since it was a long journey, he had nothing else to do, he actually made a similar calculation and found out what is now called the Chandrasekhar limit. If an object has a linear density which is higher than this threshold value, it becomes a candidate for a black hole, and no photons can escape from the black hole. It does not give out any light. So if somehow I'm standing on a black hole, I'm on the surface of a black hole or on the event horizon, I have a laser light, I shine the laser light, the photons are going to fall back into the black hole. In fact, they will not even go that far, they will just go like this. So this is actually real proof that the photon does indeed carry momentum. Now let's do a calculation for our sun, our own sun. Our own sun, this is the symbol for the mass of the sun. The mass of the sun is about 10 raised to 30 kilograms. And the radius of the sun is about 10 raised to 9 meters. So what's the linear density? It's 10 raised to 21. It's 8 orders of magnitude smaller than this limit. So our sun, when it burns out its fuel, it cannot transform into a black hole. That's very bad. The best it can do is it can become what is called a white dwarf. So in stars, everything is controlled by the mass of the star and by the radius of the star. So in the can you please turn on this for a second? I just want to end with one slide I would like to show you. In the meantime, we can have questions. Ji.
What happens to the photons which are in the black hole?
Well, we don't know because we cannot observe them. But there are different theories. If a black hole emits photons, it produces photons, it produces energy, then there are a lot of theories as to what happens. How does it change the thermodynamics of the problem? Does it increase the entropy of the black hole? What happens to the entropy of the universe? Does the second law of thermodynamics break down? So there are lots of theories which really need a longer discussion. Ji. If the black hole is producing photons and those photons are falling back into the black hole, its mass must keep on increasing, yes. Quasars जो होते हैं ना, quasars, these are neutron stars, they're just made of neutrons. एक ऐसा star है जिसमें neutrons हैं सिर्फ, electrons भी नहीं है, protons भी नहीं है, सिर्फ neutrons हैं. और सिर्फ neutrons हैं तो उसका साइज बहुत छोटा होता है, उसका रेडियस बहुत छोटा होता है, maybe a few kilometers. And when the quasar is formed or the neutron star is formed, it's formed from a larger star. So when it shrinks to a few kilometers, what's going to happen to its angular momentum? It has to increase. So there was a large star moving with a certain angular frequency and now shrinking. It's increasing its velocity. It's increasing its angular velocity. So when it increases its angular velocity, it emits pulses of light, of gamma ray photons or X-rays, and those X-rays reach the earth after regular intervals, and from those regular intervals you can tell what the frequency of the rotation is, and you can tell what the radius of the quasar is. So this is what a quasar is, or a pulsar. Now the last thing where I would like to finish this lecture, now this week is really going to be very interesting, and it is going to touch the cornerstone of modern physics. What's a wave and what's a particle? Tomorrow's lecture I am going to talk about matter waves, because we've seen that matter comprises particles, light has a wave existence and a particle existence. अभी 10:15 नहीं हुए, 1 मिनट, 11:15, 1 मिनट, सब्र, हौसला, ठीक है? तो this week is going to be very important, and I'm going to start with a discussion in tomorrow's lecture. But what I would like to show you is one picture. खामोशी से सुनो प्लीज, क्या हो गया? ये वेव का लफ्ज इंग्लिश की डिक्शनरी से आया है, मॉडर्न फिजिक्स अभी पैदा भी नहीं हुई थी. पार्टिकल का लफ्ज भी इंग्लिश की डिक्शनरी से आया है, क्वांटम मैकेनिक्स का दूर दूर तक कोई सुराग नहीं था. तो these words are entrenched into our vocabulary and they give certain meanings. So the problem in studying modern physics is that we tend to live with these words and we tend to stick to these meanings. So we have to define modern physics so that these meanings, we have to do justice to these meanings. So that's the difficulty of teaching modern physics. So I would like to start the next lecture with a discussion, but here I would like to show you a small boat that carries two seamen and they are blindfolded, आंखों पे पट्टी बंधी है. और अगर इस तरह की एक डिस्टर्बेंस आती है, एक ऐसी डिस्टर्बेंस आती है जो इस तरह दिखाई दे रही है, तो they will say that we have been hit by a wave or we are undulating or vibrating on a wave. If they see a disturbance like this, they would exclaim that we have been hit by a particle. This is our common sense notion of a wave and a particle. And the difference that you observe is that the dimensions of this boat d are comparable with the wavelength of this disturbance. Here the dimensions of the boat d are much larger than the wavelength of this disturbance. So we would like to start next lectures with a discussion of this effect. Thank you.